Last section. Okay, we're now going to look at unit 13, and we're going to look at conservation of energy. Very important. Okay, so now we're going to use the potential and the kinetic we worked out earlier and we were speaking about in the last video, and we're now going to put them together in a concept known as mechanical energy. So first of all, you know, because you've been taught this lots, that when it comes to energy is always conserved. So the total energy of an isolated system always remains constant. Okay, in fact, the total of energy in the world remains constant. Energy cannot be created or destroyed. It can only be transferred from one type of energy to another. So what we're going to look at specifically is we're going to look at mechanical energy. Okay, now mechanical energy is the sum of the gravitational potential energy of an object and its kinetic energy. This is all energy to do with its motion and its position. So mechanical energy is potential plus kinetic. For our purposes, we work with isolated systems. Now, an isolated system simply means that we don't have any external forces, no friction, no air resistance, etc. Which then means mechanical energy can be conserved. So the principle of the conservation of mechanical energy says to us that the total mechanical energy in an isolated system remains constant. So no matter how an object moves within this isolated system, the mechanical energy will stay the same. Okay? Which means total mechanical energy at a point A in a system's motion, of an object's motion, is equal to the mechanical energy at point B. Okay? So this is actually really important that you get. Mechanical energy stays constant because we are going to ignore, which is what an isolated system means, no friction, no air resistance, no external forces. We're simply allowing the object to move under gravity. Okay? So we're going to ignore everything else. In reality, I know that there's air resistance. I know that these things exist, but we obviously want you to get the principle, so we're going to make it ideal. So, energy is not lost or destroyed. We can't create it, we can't destroy it. There's a conversion that's going to happen of either potential energy to kinetic or kinetic to potential. It all depends on how the object's moving. Mechanical energy in an isolated system remains constant. I'm hoping you're understanding this is important. I've said this a couple of times already. So, the law of the conservation law is used in calculations involving the following situations. Where do we use this law? Which we said EP plus EK at one point is equal to EP plus EK at another. When objects are falling freely, in other words, we drop them or we throw them in the air. When there's pendulums are circular motion, so you can't use equations of motion. And for roller coasters, we love roller coasters, okay? I don't like being on them, but we like asking them in questions. That's what I mean by that. So roller coasters aren't straight lines either, so it's not linear motion. So if there's air resistance or friction, the mechanical energy will change as it goes from point to point. So we have to ignore it, okay? If we have an isolated system, when it's not in a straight line, we use the conservation of mechanical energy, okay? You have to start from this point. Even if something in the system is zero, it doesn't matter, you must start from here. So, let's look at an example. We have a brick with a mass of 2 kilograms. So that's 2 kilograms. It falls from a height of 45 meters above the ground. Calculate the magnitude of the velocity, v, with which it hits the ground. Only use conservation of energy. So it falls from, that's Vf, which is what we're looking for, and Vi is 0, so it's basically dropped. Okay, now I said use only conservation of energy, which means if you do it in any other way, even if you get the right answer, you're going to get 0. So, potential plus kinetic at A is equal to the potential plus the kinetic at B. Potential at A is mgh, kinetic at A is a half mv squared. Mgh plus a half mv squared. So, it was 2 meters above the ground, 9,8, 45 kilograms. I know that's 0. I still put it in. I know when it hits the ground, it's now 0 again. But now it's got a velocity. So what am I doing here? I'm solving for v. Don't forget to square root it at the end. Question was, calculate the magnitude, which means we don't need to give direction. But it would be down if we put the direction. Now, Calvin plays with a ball of mass 50 kilograms on his 50 grams. Remember, this got to be kilograms, so I'm going to have to divide by 1,000, okay, when I do this, on his toy train track. The track looks like the one in the picture, so it's like a roller coaster. It was 60 centimeters, then it goes to the ground, then it goes 40 centimeters above the ground. First question, he places the ball at a point A, and it starts to roll from rest along the track. Assume that there's no friction between the ball and the track. In other words, it's a closed system, isolated system. Calculate the mechanical energy of the ball at point A. Mechanical energy is potential plus kinetic, so mgh plus a half mv squared. It wasn't moving, so EK is 0. So you can go straight to the answer, 0.294 joules. Okay? I'm keeping the 3 decimal places because it's just going to make it a little bit more accurate. Then they say, what will the kinetic energy of the ball be at point B? Okay, you have to show me the calculation. EP plus EK at A is equal to EP plus EK at B. Half mv squared, etc. Now, I've worked this out previously. I don't have to do all the substitution again. Okay, I know the potential at B is going to be 0, but I still have to show it. So EK is 0.294 joules. Okay. Now they want the speed of the ball at C. It was 40 centimeters above, so now it has both potential and kinetic. So we're going to use A again, and now we're using point C. At A, it's 2.94. At C, it's above the ground, and I want V. We're going to solve for V. Okay, I didn't do all the maths. If you need to do all the maths, do all the maths. Okay? Remember to square root your answer at the end. Otherwise, you're going to give me an answer that's too big. Okay? Why is it not correct to use equations of motion? Because it's not linear motion. It's not a straight line. So we can't use equations of motion. Next example. If we have a lead ball with a mass of 0.5 kilograms, which is attached to a long light string and allowed to swing from a height of 1.5 meters above its equilibrium position, so that's H. Okay, so here, that's H. This is my reference point. They want the maximum velocity of the ball. In other words, when it's here, initial velocity is going to be 0. I want final velocity. It's a pendulum, so EP plus EK at A is equal to EP plus EK at B. We know it has an EP because it's at 1.5 meters above. It was dropped, so initial velocity is 0. By the time it gets to the bottom, height is 0, and we want V. Now, I put plus or minus, but actually, you know, over here, I would be okay if you just put 5.42. They want maximum velocity. Of course, it's plus or minus because it can go in 2 directions, but I would be happy if you just put the plus. Okay, so let's look at the exercise. So really what you should do now is pause the video, do the exercise, and then watch the video for the answers. Okay, a pot plant falls off, that should say off, so it should actually be OFF, off the balcony of an apartment. The balcony is 20 meters above the ground. The pot plant has a mass of 2 kilograms. So it's 20 meters above the ground. We have a 2 kilogram pot plant which falls off, so VI is 0. They want the pot's potential energy before it falls. Well, that's easy. EP equals mgh, 392 joules. It's already in kilograms, so that makes life easier, and it's already in meters. That also makes life easier. Now they want the kinetic energy just before it hits the ground. So EP at the top equals EP plus EK at the top equals EP plus EK at the bottom. Now I'm not putting in the substitution here because I know it's 0. So you don't have to put in, it's fine. We know it's 0, but you have to show it to me. So that means the EK at the bottom is 392 joules. I'm being nice here. I'm actually making the maths a bit easier for you. Right? Because now they want the speed at which it hits the ground. I know the kinetic energy with which it hits the ground. So I know it's 392, and it's a half times 2 times v squared, which means it's actually 392 equals v squared. So I've got to square root that, which is 19.8 meters per second. Very nice. It's nice and easy, okay? Daniela climbs on a stool, lifts her teddy bear of mass 0.4 kilograms to a height of h above the ground. She then lets it go. Its speed, just as it hits the ground, is 2.5 meters per second. Ignore air resistance. Question 1. What type of energy did the bear gain when it was raised to a height? It was above the ground, so that means it gained gravitational potential. They then ask you to calculate the kinetic energy of the teddy bear just before it hits the ground. But before it hits the ground, it's going at 2.5. So EK equals a half mv squared. So it's a half times 0.4 times 2.5 squared, 1.25 joules. We're good. Calculate the height. Well, EK at the top equals EK at the bottom, or position A, position B, doesn't matter. Now, again, I could have put the zeros in here instead of just doing all the calculations, but, and I'm not sure why I've got 0 there. This should be 0.4 times 9.8. So this is her height when she lifts it to. She dropped it. Velocity when it hit the ground. Now, we've already worked out that value, so I didn't really need to put it in. But you solve for h and we get 0.32 meters. Okay, we have one more question to do. Michael skates on his skateboard. Together they have a mass of 60 kilograms past point A with a speed of 6 meters per second. The surface is frictionless, so we know mechanical energy is going to be conserved. Okay, and obviously at point B he's going to be going at, well, he goes to a maximum height of 2. First question, what is mechanical energy? Well, it's potential energy plus kinetic energy. Okay. Why can't we use equations of motion? Well, because this isn't linear. Okay, this is a roller coaster. It changes direction all the time. Okay. Calculate Michael and his board's kinetic energy at A. Well, that's nice and easy. EK equals a half mv squared. It's a half times 60 times 7 squared. 1,470 joules. So we haven't done anything difficult yet. Then they ask, what is his mechanical energy of Michael and his board at B? Well, mechanical energy is constant everywhere. Therefore, it's 1,470. Remember that his mechanical energy at A is his potential plus his kinetic, and his potential at A is 0. Okay, because he hasn't moved. All right, so there we go. What principle will you use to calculate Michael's speed? Conservation of mechanical energy. Now they ask you, will Michael be able to reach point B? So basically what we want to do is say, does he get to the 2 meters? Now here you've got to make a decision. I would say to you, calculate the velocity of Michael at point B. So let's assume he gets to B, and let's see how fast he's going. Okay? So I'm going to say, oh wait, I didn't even do that. I did another way around actually. That's one way to do it. The other way around is to go, how high will he go when he stops? So what's the maximum height he can go to? And that height is 2.5 meters. Okay, so here, this would be the maximum height he could get to. But of course, the height of B is 2 meters, so he will reach B. Okay? You could also have gone the other route, as I was trying to explain, of going, well, if he gets to B, what's his velocity? And if he has a velocity at B, then he reached B. If you work it out and you end up with a negative velocity, then he hasn't reached B. Okay? Because then it means he's actually going backwards. Okay. So, now they say, if it is possible for Michael to reach point B, what would his speed be? Well, at C, mechanical energy is conserved. At C, okay, he's still 0.8 meters above the ground. Okay, we know the mechanical at A. We're going to solve for V, and he'll be going at 5.77 meters per second. All right, it's really not so bad. So, you now need to do activity 3 on page 257, question 1, 4, and 6.